Milton, is your sound working? Okay.
Ivan, I can hear you, but I can't.
Hi, Elise. So I think Milton is going to introduce you, but it says it's connecting to something. So if that doesn't work, I'll start. Milton, can you speak? Okay, so his sound doesn't seem to be working, so we'll switch it up. So I'll start. So first of all, welcome back to a new semester, our first full semester of the One World Probability Seminar. And some of the sort of short-term and long-term goals are listed here, but the real idea is to have a chance to bring people from all across the world together to see excellent speakers and to kind of try to spark activity and interaction. So we're doing a slightly different format than we did in the spring. In the spring, we were just doing two kind of somewhat disjoint talks. What we'll try to do this semester mainly, there'll be some exceptions, will be to have two talks on a similar theme, where the first talk will be more pedagogically focused, really to help introduce people to a field, get people some of the knowledge they need, some of the background. And the second talk will be more research focused. So that doesn't mean that any one of the two talks will be, better. You should attend both of them. And I think you'll get a lot out of this format. So today, to kick off the fall, we are very pleased to have Elise Guionnet and Zhongyang Huang speaking about large deviations and random matrices and spherical integrals. Just before Elise starts, the kind of general rules are that we should have a very active discussion in the chat. So ask questions, comments, all that sort of stuff. Elise might not see it, but we'll be monitoring it. And if it's necessary, we'll bring stuff to our attention. Otherwise, people can answer in the chat. At the end of the talk, we'll unmute everyone and we can all join together in congratulating the speaker and clapping. And then we can have a little bit more discussion where people can raise their hands and talk. And then we'll take a very quick break, and then we'll start with the second talk. Okay, so as to not delay things any further, let me turn this over to Elise Guionnet, who hopefully will be able to now share her screen. Let's see. And if for any reason you get kicked off, this is going to be broadcasting live on YouTube. So if the connection is not so good for you, you can always go there. Okay. Elise, can you share? Or does...
No, I can't.
No? Okay, Milton, I think somehow you need to let Elise share. As you may notice, we are not Leif and Andreas. So there's also been a transition in who's organizing this semester. So Milton, Jara, and myself are organizing. And so we're also addressing our own technical challenges as we figure out how to do it.
So I still can't. Maybe it's related with the fact that Milton is trying to record. I don't know.
Let's see.
But at this point, I don't have the possibility to share my screen.
Maybe you need to unshare. Well, right. So that's right. So now try.
Okay. Oops. Yes.
Ah, wonderful.
So,
okay.
I don't see my screen, so it's a full screen.
It's not quite in full screen mode.
Like this, it's fine?
That's better, yeah.
Okay, great. So maybe I start. So thank you very much for the invitation to talk to this great seminar. And I will talk about large deviations for large random matrices and try to give an introductory talk. So please do not hesitate to ask questions, even though I'm not super good with Zoom and with the chat. Ivan and Jiao and maybe Jonathan will be helping me through that. And you can ask also questions, and Ivan will give them to me. Also, I take the advantage of this talk to make some advertisement. I got a new ERC grant, and actually it's exactly on this topic. So it's LD for large deviation and random matrices. So in French, it reads le drame. So hopefully it's for dramatic new contribution than, than the negative side of this. Okay, so I will start by giving some introduction to the subject of random matrices and then go to a large deviation. So it's important, I think, to remember that random matrices appeared in statistics first in the work of Wishart, who introduced these random matrices to model big arrays of data with some noise. And with the question being that if you observe this data, do you really see the signal? Can you find out the signal which was at the origin, or you just see the noise? And there is kind of idea that, for instance, if you look at the largest eigenvalue of your matrix that you observe, so if it behaves like the one of random matrices, then it means that you cannot really retrieve your signal. But if it pops out, if you have outliers, maybe then some information is going through and you can try to retrieve it. So it's quite an important subject still today than in statistics, but also in machine learning to use this kind of ideas to try to retrieve signal and information for big arrays of data. The second instance where large random matrices appeared is in quantum physics in the work of Wigner in the 50s, when he proposed to approximate the Hamiltonian of heavy nuclei by a large random matrix. So the idea that these heavy nuclei are so complicated with so many particles and electrons and so on that it's very difficult to analyze them, but you can try to model all the things that somehow you can't compute and you don't really know for sure by randomness, and this gives rise to a large random matrix. And then what people are interested in is the spectrum of these matrices, which represent the energy levels of the system, and in particular gaps to know how you go from one state to the other. And so it gave rise to many questions about random matrices, namely, what is the typical spacing of random matrices and how much does it depend on the model? Is it universal? So again, it's a very active field of research nowadays, in particular after the work of Erdős, Liao and collaborators, and Tao and Wu and collaborators, who worked a lot to give the best condition for universality. So I will come back to this question a bit later. Another aspect that I like in random matrices is that the spectrum of random matrices can be seen as a kind of stereotype of strongly interacting random variables. And in fact, at least mathematically, in the same family of other problems, like for instance, random tiling. So here you look at some hexagon, for instance, and you would like to tile this hexagon with lozenges. And the point is that if you look at the distribution, for instance, of the blue lozenges on a vertical line, then it will follow a distribution which is very similar to the one of the eigenvalues of random matrices. So from this observation, you can imagine that a lot of ideas and arguments and techniques coming from random matrices could be imported to this other kind of settings. So that's also one application of random matrices. Another one, which is even more mysterious, goes back to the 70s and the conjecture by Montgomery that if you look at the zeros of the Riemann zeta function on the critical axis, so Riemann hypothesis is that all the non-trivial zeros lie on this critical axis, which is x equal to 1/2. And he conjecture based on some numerics, very important actually numerics, that the distribution of the zeros was very similar to the eigenvalues of random matrices. And so this conjecture is still a big open problem in the field, which is still very mysterious. But based on this, there were lots of other conjectures which were made and which could be solved thanks to this analogy. So for instance, a few years ago, Fyodorov and Keating conjectured that the supremum of zeta function on this critical axis far away from the real axis was behaving like some log t. So if t is the distance from the real axis, and their conjecture was based on the analogy with random matrices where the zeta function is replaced by the log of the characteristic polynomial. And this actually could be proven rigorously in this paper by Arguin, Belius, Bourgade, Radziwiłł, and Sudharayan in 2016 by using this idea coming from random matrices. So it's still, as you can see, a very active field. And the last but not least of the field which I want to mention, which are connected with random matrices, is operator algebra. And the point here is very simple, that if you take two random matrices together, they are just non-commuting. And so you can look at the algebra they generate. And what Voiculescu saw is that when the size of these matrices goes to infinity, at least for instance, if you take Gaussian matrices, so then they will be free asymptotically as the dimension goes to infinity. And this notion of freeness is really closely related with the notion of freeness on groups. So from there, random matrices became a source of intuition to better understand free group factors. And reciprocally, the setting that Voiculescu developed, which is free probability, which is this probability setup where you have non-commuting variables which are given this notion of freeness, which you have to compare to independence. So this field is very useful to analyze random matrices, because this is somehow the space in which random matrices should live asymptotically. So let me now go into more detail on less hand-waving things. Of course, before I didn't mention many other things which are related with random matrices, like chaotic systems and many other things, but I want now to give you some better idea of what are the objects we're considering and what we can say about them. So I like to consider the simplest possible random matrix, which is a n by n, and it's Hermitian. So the entries will be either real or complex. So when the entries are real, we denote this beta equal to 1 for some reason which will be clear later on. When the entries are complex above the diagonal, we denote this beta equal to 2. And so I assume these entries to be centered. So the xij are of order 1, and I divide it by square root of n so that the spectrum will be non-trivial. And the covariance of my variables above the diagonal will be 1. And eventually, in the real case, I will take 2 on the diagonal, again, for reasons that will appear to more clearly later. And so the question that we are asking when we consider large deviation is how to estimate the probability of rare events for the spectrum of such random matrices. So before talking about untypical behavior or rare event, what are typical events for such matrices? So the first result that Wigner proved in the 50s is under some condition on the moment of the entries, but which is not very important. So it's a convergence of the empirical measure of the eigenvalues. So your matrix, Xn, it's Hermitian, so it has n eigenvalues, lambda 1, lambda 2, lambda n. And then you estimate the empirical measure at a function f, which is bounded continuous. So you look at the normalized sum of the f of lambda I. And the statement is that this will converge almost surely as the dimension goes to infinity towards the integral of f under the semicircle law, which is given by this density, which is the square root of 4 minus x squared. So Wigner proved that under the assumption that the entries have all moments which are finite, but now it's known that it's true as soon as you have finite variance. If you can see actually, maybe it's clearer what this theorem means, that even if you assume that f has to be bounded continuous, you can plug here a Heaviside function, which is which will tell you that the number of eigenvalues which fall into some interval AB is going to be approximately n times the measure of the interval AB under the semicircle law. Okay, and the other thing that is now well known is the convergence of the largest eigenvalue. As I said, this is also something which is important in random matrices. And again, under more moment condition, but now by the result which was proven by Fourier and Kumloch under the optimal assumption by Bai and Yin in 1998, they proved that the largest eigenvalue converges to 2, which is the boundary of the support of the semicircle distribution. So we say that the largest eigenvalue sticks to the bulk in the sense that it could go away from the bulk. It couldn't go inside the bulk because then this would contradict the convergence towards the semicircle distribution, but it could go away, and it doesn't if you have the force moment which is finite. In fact, this result is not true if the force moment is infinite, and this largest eigenvalue will then go to infinity. So you can see that by just noticing that in this case, you can create a big entry in your matrix. So this means one of the xij to be of order square root of n with a probability 1 because you have this tail condition. And once you have a big entry, you can imagine that this can create a very big eigenvalue. So this is really what is going on. And so you see that there is kind of phase transition between what happens when you have 4 moments which are finite and when the first moment is finite and when it is not. So to summarize, what we have seen is that we have almost sure convergence of the spectrum in terms of the empirical measure, but also of the largest eigenvalue. And then in probability, we usually wonder about what are the errors with respect to this convergence. So fluctuations were studied. So the fluctuation of the empirical measure were shown to be very small, of order 1 over n. So this means that if you take a smooth function f, the sum of the f lambda I recentered will converge towards a Gaussian variable. And it's very different from the usual central limit theorem where you have to divide by 1 over square root of n. Here you don't need any normalization. So this was first proven again for the Gaussian ensembles by Johansson. And then it was shown to be universal as long as, again, the force moment is finite in a series of papers. And I think maybe one of the best assumptions is by Pastur and Litova. Similarly, if you look at the largest eigenvalue, it will fluctuate around the value 2. And this was proven by Tracy-Widom, again, first in the case of Gaussian variables, Gaussian entries. And they were shown to be of order n to the minus 2/3 with a convergence of this distribution to the Tracy-Widom law. And there was, as I said earlier, a big effort of the community to prove that this type of fluctuation at the edge was universal. And in fact, true as long as the force moment is finite. And this was by Erdős, Yao, and their collaborators, Tao and Wu. And I think that the optimal result was by Li and Yin in 2014. So, but you can wonder also what is the probability that you will really deviate from the typical behavior. And so this is a kind of question of concentration of measure. So as physicists say, the self-averaging property, that you can show that the probability that this empirical measure will deviate from its expectation by something which depends on just on the Lipschitz constant of f, is going to be bounded and to be extremely small. It's going to be smaller than exponential minus some positive constants times n squared times delta squared. So here, actually, you see that this is consistent with the fact that you have a central limit theorem with no renormalization just by changing delta and 1 over delta. And so this is true. We proved this to be true with offer about 20 years ago when we assumed that Bloch-Sobolev inequality is satisfied by the entries or are compactly supported if we replace here the expectation by the median. And this is just based on the fact that these quantities are nice Lipschitz function of the entries. And then you have this kind of meta theorem due to Talagrand and Erb's argument on Bakri-Emery, all these kind of things, which tells you that if you have a smooth function of independent variables, then it will self-average. So this result was really an application of this general meta result. There is actually a very nice result which extends this result by Bordenave, Caputo, and Chaffai. And what they prove is that actually to have self-averaging, you don't need to have any assumption on the moments of the entries. So you just need independence of the entries, and actually even less, you need independence of the rows in your matrix. But for this generality, you need to change the speed. So here you don't have the n square in the right-hand side, but you have an n. And so this is not compatible with a priori, well, this is not in the direction to have a strong central limit theorem as before. And indeed, if the entries of your matrix have eviters, the central limit theorem is in the scale 1 over square root of n, like the usual central limit theorem for independent entries. So this speed is consistent with this kind of result. So that's about concentration of measure, and as you can see, it's very universal statements. And so what I wanted to talk about is more precise estimates, namely large deviations. So in large deviation questions, you don't want to estimate the probability to deviate from the typical behavior, but you want to estimate the probability to have really another behavior. So that your empirical measure, for instance, will be very close to some profile mu, which is here, this thread, which is very different from the semicircle law. So you would like to estimate this kind of probability when first n goes to infinity and then delta to 0. Okay, so in general, I will denote this kind of small ball property by saying that the empirical measure is in some kind of small, is close to mu in this sense. Okay, so this will be the notation. And similarly, you can wonder what is the probability that your largest eigenvalue go away from 2, and this could be, of course, much farther. So I am going to tell you more or less what are the kind of results that we have and open problems. So the idea that as for fluctuation, when you have Gaussian entries, everything is more simple because the joint distribution of the eigenvalue is well known, and then you can work just on this density. So from this exact formula, as I will show a bit later, you can derive a large deviation estimates. When you have heavier tails than the Gaussians, so which means that your probability distribution of the entries decays like some stretch exponential, then large deviations are due to large entries, a bit like the largest eigenvalue when you have force moment. So you can create deviation very easily by having large entries in this case, and then you can again derive large deviation principle. And then the question which was open and which still partly open is what happens if the entries are sub-Gaussian. And so in this case, there is kind of transition between these two type of large deviations between the Gaussian and the Evertel that I will describe a bit later. And the proofs are quite different. Again, they go by tilting the measure. So is there any questions? Because now I'm going to go into the details of type of result and large deviations.
Yeah, so Alice, there was a question on the chat about what do you mean by nonlinear large deviations?
Okay, so I think I will not, so nonlinear large deviation is when you want to have large deviation for a function of independent entries, so which does not need to be like a sum of independent entries, okay? And so fortunately, I think next week, Shoaf is speaking to the seminar, and with Amir Dembo, they were the fathers of this theory. So with some chance, you can know much more next week about nonlinear large deviations.
There is another question about a reference for the heavy-tailed large deviation just mentioned.
So I'm going to precise now all the results. So it's Bordenave and Caputo and Ogeri, but I'm going to be much more precise. I mean, it was just kind of overview of, yeah. That's it. Okay, so why are Gaussian ensembles, so entries with matrices with Gaussian entries much nicer than the others? So the idea that they have lots of invariants. So if you have a matrix filled with Gaussian entries and you multiply it left and right by a unitary matrix or orthogonal matrix, well, your entries will still be Gaussian because the sum of Gaussian, and you can check that the covariance will be the same as the one you started with. So this means that somehow the law of a Gaussian Wigner matrix is invariant by conjugation by unitary orthogonal matrices. And this is why somehow, well, this is related with the fact that you can compute explicitly the joint law of the eigenvalue. And to do that, you can decompose your matrix Xn as some diagonal matrix where you put the eigenvalues of your matrix times some unitary. And so you can just fix some parameterization of these unitary matrices will follow the R measure. And then you do the change of variable to change from the law of your entries, which are just Gaussian, to your diagonal, your eigenvalue, and your unitary matrix, your parameterization of the eigenvectors. And when you do that, what you find out is that you have a Jacobian, which is, so you have first, of course, a Gaussian term. So the choice of the covariance of the matrix is just made so that the trace of Xn square is just the sum of the eigenvalue, the sum of the Gaussian terms is just going to give you the trace of Xn square. So this gives you this term. But then when you do the change of variable, you have also some interaction between the eigenvalues, which is this Jacobian term. So this is not very difficult to see, but it's very crucial because you see that the eigenvalue are very strongly interacting. I'm saying very strongly because you see that you have n squared term. So your interaction is of size exponential n squared, whereas usually if you look at entropy of the probability that you have under the independent random variable, all volumes will be of size approximately exponential n. Okay. So what I mean is that under this kind of measure, somehow the interaction will be crucial and will really lead the behavior of the eigenvalues. So from this formula, now I'm claiming that it's not very difficult to get large deviation for the empirical measure of these eigenvalues and the largest eigenvalue. So again, we look at this empirical measure of the eigenvalues. So it's just a probability measure on R. And then the statement of the large deviation principle is that so the law of this empirical measure satisfies the large deviation principle with spin n squared and good rate function, which is given by beta times some function g of mu minus the infimum. So g has this explicit formula. And what this means, so saying that it's a good rate function means that the level set of E are compact. And the large deviation means that you can bound from above the probability that your empirical measure belongs to some set A by minus the infimum of the rate function over the closure of A. You can lower bound it by the lim inf, and you have the lower bound by taking the interior of A. Okay, so that's really the statement of the large deviation principle. Now, the main point in the large deviation principle is when you take A to be a small ball, so a ball centered at mu and with radius delta. And then what you will see that you have the infimum over your ball of your rate function, which is approximately your rate function taken at this measure mu at the center of your ball when delta goes to 0. Okay, so somehow a large deviation principle mainly states that you have a weak, what is called a weak large deviation principle, that you can control the probability to be of small balls. Okay, and here, so this rate is just a double integral of some function. So this function is lower bounded, so it's always bounded from below, and so this is always well defined. And you can check it's a good rate function, and also you can check that it is minimum at a unique probability measure, which is the semicircle law. So from that, you can prove again that you have convergence towards the semicircle law, because the infimum on the complement of any ball around the semicircle law will be strictly positive. So this means that this probability will declare like exponential minus n squared if A is a complement of any small ball around the semicircle law. So let me give you some idea of the proofs. So again, this is the ideas are not very difficult because you have this explicit law. So for the point, as I say, that you want to estimate the probability of small balls and show that it is given by this exponential of minus n squared times your rate function. And to do that, you look at your distribution. Okay, so your distribution has this Coulomb gas interaction on this Gaussian weight. And the idea is that you can put everything in the exponential. So you will have the log of lambda I minus lambda j. And here you will have lambda I squared. And if you do that, you realize that you can write your density of exponential minus beta n squared times some g, which I put with some sign to say that it's out of the diagonal, taken at your empirical measure. And here you have some leftover here because you have less term. So what is this? What is this term? So it's just the integral. It's like the g before, but you are taking the double integral over x and y outside of the diagonal. So it is just because, of course, in the definition of your density, you don't take diagonal term because otherwise this would be 0. So at this point, the idea is that, well, you should still think that for most measures, this diagonal, for instance, if you have measures which are absolutely continuous with respect to Lebesgue measures, this diagonal will not matter. And so you can think that this guy is not far from the G we had on the other slides where you didn't have this complement of the diagonal. Moreover, you can imagine that this guy is continuous in the measure. Okay, so this is not really true because this function is unbounded. If it was bounded, it's bounded continuous, this would be a bounded continuous function. But okay, let's imagine still it's continuous. So if it's the case, then when you look at the probability to be close to some measure mu, well, this part of the density would be fixed. Okay, so it's really Laplace method. And so you could just factorize it. And here you will have just some probability measure, the Gaussian law, and you would look at the probability of small ball under the Gaussian law. And you know it's of order exponential n, at least if the entropy with respect to the Gaussian law is finite, but in general, you can always bound it by some n log n, okay, which is much smaller compared to this. So you see that the whole, here we are more or less done. As soon as we can prove that somehow this diagonal is not important, And even though G is not really continuous, it's sufficiently continuous so that you can conclude. So it's really the heart of the proof to deal with these 2 points. So that's the end of the proof, somehow. And for the largest eigenvalue, you have the same kind of reasoning. And why? Because again, you have a nice explicit formula for the density. So what you do is that you integrate your previous density over all the others eigenvalue, which are smaller now than this x, which is your largest eigenvalue. So you integrate over that. And the law of the other eigenvalues, they look very much the same as before. Okay? It's just you have factorized the interaction with all the other eigenvalue. And again, now you can see that you can put this term in the exponential. And what you will get is the sum of the log of lambda I minus x. But this lambda I, they follow this kind of, the eigenvalues of this kind of smaller matrix. And so you can see that it's going to be very close. The empirical measure of this lambda I will be very close to the semicircle law. You can use a concentration of measure, for instance, to prove that, or the previous large deviation principle. And so the idea that in the exponential, you can replace the empirical measure of this lambda I by the semicircle law. And then again, you are done because you see that your density is just a nice function of the point times n. So you can use a Laplace principle to just conclude that you have a large deviation principle with this rate function. Okay, and then you have a little bit of algebra to see that this minus some constants is just this formula. Okay, so that's for the Gaussian case, but of course, as I said, there is only for Gaussian matrices that you have a joint law for the eigenvalues. So otherwise, you have to find other ways. And so this is this very nice results by so Charles Bordenave and Pietro Caputo, and then Fanny Augeri, in the case where the entries have a heavy tail. It's not really heavy, it's just heavier than Gaussian. So if you look at this, so here Xij is my big, the entry of my matrix. So this is a small Xij in my former notation. So I'm just saying that my entries decay at infinity. So the probability that they're greater than t is like exponential minus a times t alpha, where alpha has to be smaller than 2, in between 0 and 2. Okay, so if you have alpha equal to 2, you have just a sub-Gaussian distribution, but if alpha is smaller than 2, you have something which has heavier tails. And so what they prove, which is kind of reminiscent from the concentration of measure result, is that the large deviation for the empirical measure is not on the speed n square as before, but it's 1 n1 plus alpha over 2. Okay, so here alpha is smaller than 2, so it's smaller than n squared. And they have some expression for the rate function, which depends only on alpha. And this was complemented by Fanny Augeri to get a large deviation for the largest eigenvalue, and showing that the speed was of the rate was n to the alpha over 2. And so here the ideas are very different from the Gaussian case because you don't have this explicit formula. And so I will not tell you about nonlinear large deviation. I hope that Shoav will do that for me. But just why you have a different speed for your large deviations. So the idea that you can create deviation much more easily just by having big entries. So as before, if you want to have to create a big entry, to create a big eigenvalue, it's more or less enough to create one big entry in your matrix, because then your matrix will have typically lots of small entries on one big entry, which will push the spectrum in the direction of this big entry. And what is the probability to have one big entry in your matrix? Well, it's exactly exponential minus a t alpha and alpha over 2 to have an entry which is greater than t. So you see that the probability to have an untypical behavior for the largest eigenvalue should be of this order. So of course, then you have to show that this kind of strategy is optimal to really get the large deviation principle, but at least this show why you have this different speed. And it's very similar for the large deviation for the empirical measure. The idea then is that if you want to change your empirical measure, you should change at least of some constant times n entries, because otherwise by Weil interlacing property, you will not change the empirical measure. And to do that, well, you should change exponential minus, this will have probability exponential minus n to the power 1 plus alpha over 2. Okay, so that's the same type of idea. And again, getting the exact trait is much more involved. So that's the idea of the proof, and the references were over there. Okay, so now the question, of course, is what can we do about sub-Gaussian? So sub-Gaussian, there are lots of measures which are sub-Gaussian. You have also compactly supported entries. And at this point, we have no clue how to do anything. So I will tell you about some results for the largest eigenvalue. And so sub-Gaussian here will mean that if you look at the Laplace transform of the measure mu, which is the distribution of your entry, let's say that they're all IID and real to fix the IDs. So this will be bounded by exponential a t squared over 2 times so the covariance, which is here 1 or 2. Okay, and so that's for sub-Gaussian, and then we introduced a notion of sharp sub-Gaussian on a measure. And this is the case if and only if a is equal to 1. So here you should remember that this inequality should hold for all t. And so when t is small, you know that the best a you can take is 1, just by expansion. Okay, so a has to be greater or equal to 1, and it's sharp sub-Gaussian if you have equality, if a is really equal to 1. So fortunately, you have nice examples for this property to hold, and this is the Radmacher law. I mean, you can check that the Laplace transform is just a hyperbolic cosine, and which satisfies this property with a equal to 1, and also the uniform measure. But you have many actually examples of measure which do not satisfy this. And for instance, you can multiply a Gaussian variable by a Bernoulli, and it will not satisfy this kind of inequality with a equal to 1. Okay, and so what we proved with Jonathan Husson is that in this case, so if we have sharp sub-Gaussian tails on some technical hypothesis, then we have a large deviation for the largest eigenvalue. And the rate function is exactly the same as in the Gaussian case. So it's kind of surprising, because usually large deviation depends on the measure themselves, but in this case, you have some kind of universality of large deviations. And of course, then you would like to understand what happens in the general case. And so in the general case, you don't have universality. So in the general case, you have some finite A. And what we could prove, so with Fanny Ojeri, is that under some additional technical hypothesis, I will not describe here, but you can find it in the paper which is on the archive. So the law of the largest eigenvalue satisfies large deviation estimate. So this means that you can estimate the probability of small balls, but only for some x. And namely for here for x large enough. So if you look at deviations which are big enough, you can estimate the probability that lambda n will be close to some x by some exponential minus n times some rate now, which will depend on mu, which is the law of your entry. And in fact, you can see that it's not the same rate function as the Gaussian case, because when x goes to infinity, I behave like x squared over 4a. So the behavior at infinity depends on a. Also, if in the case where a is not too big, and for x which are close enough to 2, which is the boundary of the support, the rate function equals the Gaussian rate function. So you have really a transition, and the point is that the proofs to obtain this kind of result are really different. In one case, in the first case here, the argument that you have are much or kind of closer to the Evitel argument in the sense that you try to localize some entry of your matrix to make some entries bigger. Whereas in the Gaussian case, the best strategy to do deviations is really by doing some very mild change to all the entries. So that's somehow the idea. And at this point, we cannot really control what happens at the transition between these two mechanisms. Okay, so I will give you some idea on the proof, which is quite different. So it's closer to a Kramer's argument, which is done by tilting. So tilting in large deviation theory is just try to change your measure by changing the density to make the desired deviation more likely. Okay, and the idea that we had was to tilt our measures by what is called spherical integrals. So you can think of it some Laplace transform of your matrix, but you evaluate this matrix at a random direction E, where E is following the uniform measure on the sphere. Okay, so this can really be thought as some kind of Fourier or Laplace transform on the space of matrices. And what will be useful for our analysis is to understand the asymptotics of this kind of spherical integrals. And actually with Mil and Maida, we prove that so if the matrix X here has a largest eigenvalue which converge over some value, and its empirical measure also converge, then we can estimate this quantity as n goes to infinity. So here the idea that it should depend on the largest eigenvalue, because when theta is very large, the idea that your vector E would like to align on the eigenvector for the largest eigenvalue. That's kind of the most typical thing that will happen, and so then it will depend on the largest eigenvalue. Otherwise, it won't. And maybe just to say that this kind of results are not very difficult. I mean, it looks a bit mysterious because you have this uniform measure, but at least if X has only finitely many different eigenvalues, you can write this scalar product as the sum of the eigenvalues times some gamma I. Gamma I is just the L2 projection of E on the eigenspace corresponding to this eigenvalue. And you have a joint law for these guys, the gamma I. They just follow some Dirichlet law. And then when you look at your spherical integral, it will just be the integral over the sum of this gamma I equal to 1. Okay, so the sum of the gamma I is equal to 1 because the Vj here are just the eigenvectors of this Laplace transform under this weight. And then the sum of the Ni has to be n. And you can use just Laplace method to estimate this guy. Okay, and then you can just compute this supremum and you will get some nice function of your largest eigenvalue and the empirical measure. So it's not very difficult, and yet it's quite crucial in our analysis. So let me give you, so I have two slides more about this proof. It just gives you some idea on the large deviation principle in the case where we have a sharp sub-Gaussian entries. And so as I said, the main idea is to try to tilt the measure. Okay, so we tilt the measure by this spherical integral, and so the point is that we multiply and divide by this spherical integral. So here we did nothing, but then we notice that under our law, the empirical measure of X is going to be very close to the semicircle law. I mean, in the scale n squared, so I can assume that my empirical measure is close to the semicircle law because it's with really overwhelming probability. So these guys are actually more or less constant. So I just remove the a lower bound. So this gives me this weight that I just estimated the time before. And then I do an upper bound by neglecting this indicator function, and then I get the expectation over the matrices of my spherical integral. Okay, so now I want to estimate this guy. Well, I just plug back the definition of the spherical integral, which is here, and then I exchange integration over x and e. And when I do that, what I find is the Laplace transform of the measure of the entries, okay, integrated over e. And now I can use my hypothesis, which is this sharp sub-Gaussian hypothesis, to bound this by the Gaussian term. Okay, and what I find is just this will be bounded by the expectation of theta square and ei square et square. And when I just sum all of them, because the vector E is on the sphere, I just get some formula, which is just exponential n theta square. So then I can take the logarithm, divide by n, and take the limit n going to infinity, and then optimize over all choices of theta. And actually, it happens to be the right upper bound. So it's just, you just find the right function for the Gaussian case. So what do you do for the lower bound? Because of course, when you get an upper bound, the main question is whether it's sharp, and you can get the same lower bound. And so to see that, what you do is that you go back to the previous computation. So you multiply and divide by your spherical integral. And then you don't do any estimate. So you just remember that this is a constant, or almost equal to exponential n times j. And then before we forget about this indicator function, we keep it, and we multiply by the expectation of the spherical integral. So to get a sharp bound, what we need to do is to get the lower bound, the same lower bound as the upper bound we had before, as is exponential n theta square. And here we need to show that this is not going to be too small, so it needs to be smaller than n. And so this means that for any x, I can find a theta so that this is not going to go to 0 like exponential minus n something. So it has to go to 0 more slowly. And so for this guy, and I wanted to show it to you because this is somehow the essence why the sharp sub-Gaussian case is nice. So for this guy, well, you put back the definition of the spherical integral, which is this expectation over E. And then you can put an indicator function, the indicator function that your vector E is delocalized, all the entries are small. So you should remember that these vectors are taken uniformly on the sphere. So typically they are all of order 1 over square root of n. And you can make sure that actually with high probability, the L infinity norm will be bounded by n to the minus 1/3. So why is it nice? Because if I look at the Laplace transform I was computing here, what happens is that these entries are going to be small because I have a square root of n, and here I will have n to the minus 2/3. So here what I'm looking at the Laplace transform of mu near the origin. So then I can use my the expansion near the origin. And so this will be the same as the upper bound I use for the sharp sub-Gaussian case. So this is why I find a matching upper bound. In the case we consider in general, this is not true that the integral concentrate on delocalized vectors, and so the analysis is much more complicated. And for the second one, for this guy, it's a bit the same idea. You exchange integration over x and e, and you find that it is enough to lower bound the probability that the largest eigenvalue will be close to x when you have tilted your distribution not by the spherical integral, but just by exponential n theta exe. And so what is nice here is that this change of measure is just linear. So under this new measure, you see that the entries will still be independent, okay, just because it's factorized. And in fact, so they will be independent, and their mean will be changed a bit. Actually, you can see that the mean of this guy under this tilted measure will be theta E transpose. But otherwise, the covariance will be approximately 1 over n as before. So under this tilted law, your matrix looks like a GUE matrix, a Wigner matrix, with some one-dimensional perturbation. And then we have a very nice result by Bike, Benarous, and Péché, which show that for this kind of matrix, the largest eigenvalue will converge to theta plus 1 over theta, so if theta is big enough. And so this will go to 1, provided you choose theta satisfying this equation. And so this completes the proof of our result with Jonathan. So let me just conclude. So first, there were lots of extension of this kind of techniques to cases where the matrices, the covariance of the matrices depend on the site, to cases where you look at the sum of one random matrix plus a deterministic diagonal matrix, to unitary invariant ensemble. You can also get the joint large deviation principle with eigenvectors, and also do multidimensional analogs of this kind of results. So there are this is just to say that this kind of techniques I just showed you is quite robust and extends to many cases. But I didn't tell you anything about the empirical measure because actually we don't know. So we still don't know what we should expect for the large deviation principle for the spectral measure of Wigner matrices when the entries are sub-Gaussian. It should not be universal, at least not the same kind of universality, because if the entries are plus or minus 1, for instance, with probability 1/2, then you can see that the probability that the empirical measure is close to the Dirac mass at 0 is bounded from below. I mean, because if you have a matrix which is field of +1, all the eigenvalue will be 0 except 1. So the empirical measure will be very close from delta 0, and this is a lower bound by 1 over 2 to the n squared. Whereas in the Gaussian case, this is much smaller, so the entropy is infinite. You should take it at 0. So at this point, we have no clue what should be the large deviation for the empirical measure. What would be nice also would be to understand better large deviation for when you have several matrices, but I have no time to give any details on that. And so we could not do this Wigner matrices, but so with Jiao Yang and Serban Belinci, we worked on other models of random matrices to try to obtain large deviation principle for the empirical measure. And so this will be the subject of Jiao Yang talk. So thank you very much for your attention. I hope I didn't pass my time.
Well, thank you very much, Elise. So everyone should be able to unmute yourself. So if you'd like to, you can do so right now and join me in applause. And thank you, Elise. So we do, we're near the end of the time, but if there are one or two quick questions that people want, feel free to ask them now. Let me ask one because I have a list of a few. But for the lower, so you showed some universality of the upper tail of the top eigenvalue. Is there any hope for understanding the lower tail of the top eigenvalue? Not proving a full large deviation principle for the empirical measure, but at least for kind of compressing it into the bulk a little bit, showing that it has this sort of Tracy-Witten behavior for small enough displacement.
Yes, you are right that it should be either to prove to estimate the probability that the largest eigenvalue go inside the bulk than doing really full large deviation for the empirical measure. But at this point, yeah, I don't see how to attack these questions. Yeah.
Any other questions?
Yeah, I have a question, Alice. So this condition about sharp Gaussian is related somehow to log concavity or some other geometrical condition.
Yes, well, when we defined it, when we found out that this property would be very useful, I thought that people would have used it earlier in mathematics somewhere, and I asked many people, in particular in functional analysis and kind of coercive inequalities. But so far, I didn't see. I mean, I didn't see any particular study or using this property precisely. I find it curious because somehow it's a very natural observation that when I mean that this property should be useful.
Yeah.
And yeah. What is what is kind of interesting is, I mean, at least in our analysis, is that we see that large deviation change nature somehow when A is going to be greater than 1, because then really you want to have more localization, you want to create big entries. Whereas if you are really like in this Gaussian kind of upper bound, all your entries want to act collectively to create a deviation. So, but yeah, I mean, if anybody in the audience ever saw this kind of inequality used, I would be very interested, because also we made up this name, and a lot of people said it looks like a good name for it, but I didn't see any other use of this inequality.
Well, so maybe we will take a 2-minute break and transfer over to the second talk. So let's, Elise, if you unshare your screen, then we can transfer to Jiayang.